Got it. Okay, so going to do some. Oh, great. Sorry, one second. My pencil's not connected. It's weird. Could the Zoom be interfering with the pencil? If my pencil was working a second.
Recording.
Here,
Are you
this might
able
fix
to
it.
attach the pencil to the charging port for half a second? Sometimes my pencil doesn't connect and that usually
Yeah,
fixes that.
this might have fixed it. There we go. Good. Okay. I'm still broadcasting, right? Okay, cool.
Yep.
Well, anyway, so today we're just going to go over some of the basic homotopy theory needed, at least it seems, to read Ravenel, which is based, I think, on his sections 1, 2, 5, and his appendices. We're not doing anything really too fancy, say with spectra in Ravenel, so there's nothing too crazy that we have to go over, but I don't know, there's a lot that isn't, say, in 5G5 and 5G6. And also his presentation of the material he says is prerequisite is sort of all over the place in these sections. So hopefully I can give it sort of more coherently. I'm going to make some assumptions about what we already know. Namely, I'm assuming we all know about at least basic homotopy groups, and just homotopy equivalence, homology and cohomology, basic definitions, Brown representability. Also going to assume most of us understand the loops and suspension constructions for spaces. And that should be all I need to assume. Most of what I want to talk about is at the spectrum level, but there is one thing that Ravenel covers that is important for what he does that I'd like to talk about, which are cofibers of maps of spaces. Oh, and by the way, I will have probably finished by tonight fairly complete notes about whatever I talk about today and some review of other background material that I'll send to you all. And I'll try to include also references to where in Ravenel he talks about various things, because like I said, he is a little bit all over the place. And I'll try to also reference Concise or Adams's book as need be. So as for cofibers, the idea is fairly simple. So suppose it's given a map of spaces, f from x to y. We define its cofiber as a space I'll call CF. And the idea is simply to take a cylinder on the domain X, and we're going to attach one face of that cylinder to Y along F. This is meaning that we're taking the disjoint union of the cylinder and Y, and we're just identifying the points X times 1 with their images under F. Great. And if everything here is based, we're additionally also identifying the base point x naught times the interval, which does not make a significant difference. It just gives us a base point. And the point is that now we can look at the map F, and there's a canonical inclusion from Y into the mapping, the cofiber of F. I'll call this, say, IF. And what we can do now is we can look at the cofiber of this map again, and this will again yield a canonical inclusion of the cofiber into the cofiber of the inclusion of the previous one. And if you just sit and look at this definition for about a minute, you'll realize this is homotopy equivalent suspension on X. And what we can do now is we can hit the suspension on X with the suspension on the original map F. And we can iterate this forever. And we're going to end up with new map, the cofiber on suspension of F. And this goes on and on. And the point, we're going to make a definition here, is that we're going to call this the cofiber sequence generated by F. And we're going to call sequences of this form cofiber sequences. Great. And the idea is that, at least when we're working with pointed spaces, actually, well, we don't need pointed spaces for cofibers, but when we're working with pointed spaces, we should think of cofiber sequences as long exact sequences of spaces. And this idea up to homotopy does check out, because any two maps in a cofiber sequence up to a homotopy equivalence are just the composite of an inclusion and a quotient of its image. And really the basic and important property of cofiber sequences is the following. And it is that it really does induce a long exact sequence on homotopy classes of maps. So if you're given a base space Z, there's a fire alarm in my building. Can you guys hear it? Is it really distracting? Okay, so
You can hear it a little, it's not that distracting.
Let me move my laptop somewhere a little bit quieter, maybe. But anyway, given a base, let me turn the background noise suppression on high. 1 second. Oh. Where is the? Ah, here it is. Audio settings. All right, I turned the background noise suppression on high. I don't know if that helped at all. Well, anyway, given a base B, I won't write out the whole new sequence, but if we hit everything, if we hit a cofiber sequence with the thing that takes homotopy of class maps into Z, namely this, we're going to get a sequence of pointed sets. The point is, the statement of the proposition is, this gives us a long, exact sequence of pointed sets, or of groups.
A couple of questions. First of all, is it possible to zoom out a little bit of the screen? Because we can't see everything that you're writing.
Oh, I see. Okay, sorry.
Yeah, we don't see your whole screen. That's the thing.
Can you see everything now?
Yeah, that's better. Okay, and then the other question is, there's a question in the chat by Sai, if you want to read it.
Yeah, about the negative. Some sources put the negative in there, some don't. I think it is supposed to be.
What does it mean for it to be negative? Like,
sorry, Sai, I can't quite hear you. 1 second. Let me turn the volume up.
Sorry, what is going on? Can you hear me now?
Let me make you a little bit louder. Yes.
Okay, so I guess the question was like, What does the negative there mean? Does it mean that if I take the suspension, like, and I take, like, say, I don't know, some homology or something like that, like, uh, and I try to like take the isomorphism with a star of x, it has a negative sign in front of it. Like, what does it mean? I'm not sure.
I think somewhere in concise, if I'm remembering correctly, it came down to how he parameterized something over crossing with an interval. As for how that changes its effect on homology or somewhere else, I don't actually know. Does
Okay,
anybody else
okay.
know?
Yeah, don't worry about it. Same.
Okay. Oh, great. The fire alarm just stopped. And hopefully if there were fire, the fire also stopped. Anyway, if we hit this all with take a homotopy class of maps into Z, then we're going to get a long exact sequence of pointed sets. And once we actually hit sigma x, this gets a group structure because maps out of a suspension have a group structure and groups to the left of suspension of x. And so at that point, we don't just get pointed sets, we get groups, and we do in fact get a long exact sequence of abelian groups past that point, or sorry, of groups past that point.
The
And what I
screen
mean
is
by
cut off again.
okay. Wait, really?
I mean, now it looks like we can see most of it. Yeah, that's what better.
Oh, sorry. I had part of okay. I figured out what was doing that. Anyway, and what I mean by a long exact sequence of pointed sets is that we think of the constant map to the marked point as 0. Anyway, it's not cut off right now, right? Okay, great. And that's really all I wanted to say about cofibers. There's also a dual notion of fibers, but it's not essential to how we treat everything else in Ravenel. And in any case, good sources for this are they are treated in Ravenel. They're also in Concise by Peter May. And Peter also talks about fibers adequately. And now I want to move away from spaces and talk about spectra. Again, we're not doing anything too high tech in Ravenel, so we don't really need a fancy definition of spectra. We need a working definition. And so let me just, for completeness, start from the basics. For no other reason than to fix notation. We're going to define a spectrum to be a collection of spaces and maps, which we call structure maps, from the suspension of each space to the next space. Now each of these maps has an adjoint, and if the adjoints if they're all weak homotopy equivalences, we call the spectrum an omega spectrum. Great. That's the basic definition of a spectrum. Maybe the way to motivate this particular definition is, well, one way I guess is if you asked what kind of structure does the collection of maps representing reduced cohomology theory get, the answer is a spectrum or an omega spectrum. Another way to look at it is just to say that a lot of classical theorems like the Freudenfeld suspension theorem tell us that we ought to care, if we care about homotopy, we ought to care about things that are stable with respect to suspension. And once you have a homotopy category of pointed spaces, you would really like then to be able to invert the suspension functor. But on spaces, it's highly non-invertible. Not all spaces are suspensions of other spaces. And if you just look at the definition of spectra, you think, yeah, this is just the most obvious way to fix that problem. And indeed, on the homotopy category of spectra, you do get an equivalence given by the analog of suspension perspective, which we'll talk about in a second. Anyway, we have spectra, and probably the most important thing ever is the smash product of spectra. It's also very hard to get a definition right. This is one of those things you could talk about forever. Let's just give the working definition. So I'm going to say let E and F be spectra, and let X be a space. We're going to find smash products like so. Oh, and by the way, in the definition of a spectra, we're assuming all our spaces have CW homotopy type, which means that they have some homotopy equivalence with a CW complex. Anyway, about smash products. First, we're going to define the smash products of two spectra. This is considered the naive smash product because it doesn't work in full generality, but it will work for us. The 2 nth dimensional space will simply be the nth space of E smash on the space level, the nth space of F, and the 2n plus 1 space will be the suspension of the nth space of En smash the Fn space. And somewhat more easily, we can also define the smash product of a spectrum with space. We'll define that as E smash X as having as its nth space simply the nth space of E smash X. And all the structure maps here will be the ones you get induced by suspension 1 knot. Great. So we have a spectrum, and we have this very important operation of the smash product of the spectrum. The last basic component we will need are maps of spectra, which are, again, kind of this thing that are frustratingly tricky to define. Ravenel does not bother giving the full definition that you might find in atoms. What works for us, and what Ravenel tells us to do, is that, okay, on one level, he's saying a map F from X to Y of spectra. We're going to find that to be, okay, on one level, it's going to be, we would like a map of spectra to be maps between component spaces that are compatible with the structure maps in the obvious way. Those do give examples of maps of spectra, but full definition is more general. Some people call those sorts of maps sequential. Ravenel's idea is to say, let's just call a map of spectra a sequential map from X, not to Y, but to a homotopy equivalent replacement of Y by a loop spectrum, by an omega spectrum. And what does that end up looking like? Well, a map of spectra from F of X to Y is going to be defined as a collection of maps. Compatible maps with the structure maps. F sub n, each from the nth space of X, not to the nth space of Y, but to the colimit taken over K of the kth loop space of the Fn plus kth space of n. Where does this come from? Well, forgetting about the rest of the definition for a moment. If you just take this sequence of spaces for each n, somewhere in the whole taking colimits and loop spaces, you get structure map. These spaces actually are the component spaces of a spectrum that is, first of all, an omega spectrum, and second of all, homotopy equivalent to Y. Oh, I wrote F. I meant to write Y. This should be Y.
I have a question.
Yeah.
In the dimension, if in the definition for the smash product in the odd spaces, doesn't matter where you put parentheses.
In the definition for the odd spaces here. Sorry, what do you mean by the parentheses?
Like on the right side, like are you taking the suspension of En or are you taking the
Oh,
suspension
yes.
of
I'm taking the suspension of En here. And does that matter? Let's think about
It shouldn't homotopy matter because it's just smashing with S1. So it's just homotopy
Yeah, you're right.
associativity.
Okay. Okay, so anyway, this is the map of spectra as far as we're concerned. And now we can define a homotopy. Whoops. If we have two maps of spectra, F and G, a homotopy between them is, at least on a symbolic level, what you think it would be. We're going to take the cylinder on X, and we're going to say that a homotopy between them is a map from the cylinder to Y, such that composing with the inclusion of each endpoint respectively gives you F or G. And what this comes down to formally is that it's a map from the quote-unquote cylinder spectrum, which is just X smash the interval with a disjoint base point, to Y, with the property I just described. Composing this map with the inclusion of either endpoint gives you F and G. Great. So there's all the basic structure for spectra we'll need. Here are some examples. I'm also going to give some more examples in the notes that I send out. But for the sake of time, let me just give the ones that are maybe most important to everything else we'll talk about. So let E be a spectrum. X is space. I'll give 3 examples. The first is I'll say this: for every integer, positive or negative, we have the suspension, the ith suspension or shift spectrum of E, which we write as sigma IE. And that's simply defined to have as its nth space the nth space of E plus I. We also have the suspension spectrum of space, which we write as sigma infinity of X, and that is defined to have as its nth space just the nth suspension of X, and the structure maps in this case will just be the identity maps. And we have particularly important suspension spectrum, the sphere spectrum. Which we define simply as the suspension spectrum on the 0 sphere, so 2 disjoint points. Great. Those are all the examples we really need to know. Now that we have all these basic definitions, what we want to talk about next is homotopy direct limits of spectrum. Let's just some of my coffee before I do this. I'm going to say suppose is given. A collection of spectra. I'll write X alpha. This can be infinite or finite, whatever. when we have a collection of pointed spaces, we can build their coproduct as their wedge. We can do an analogous thing here. We're going to say that the coproduct of these X alpha we're going to write this as, well, I guess we could just write it as the actual coproduct of X alpha, but this turns out to be equal to, and as we'll write it, the big wedge over alpha of all the X alpha, which we're going to find to be a spectrum whose nth space is the wedge over the nth space of each spectrum, as one might expect. So I guess what we're really defining here is this symbol. This is a spectrum which we are defining to have at its nth space the wedge of the nth spaces of all the spectra in question. Taking coproducts is very nice and well-behaved, and talking about the homotopy direct limit as a consequence is in general pretty easy. So taking coproducts commutes with smashing with a spectrum. So taking homotopy groups, the homology and whatnot. Oh, right. Got to make a million definitions now. That now once we define, let me move 1 second. Once we've defined all this basic stuff having to do with spectra, I can give you a million definitions. All very easy. The first being, let's see, what do I want to start? Homotopy. Given a spectrum, it has homotopy groups. These are defined to have the kth homotopy group of the spectrum E are defined as the colimit over, I think I should use n in my index. The nth homotopy groups of the spectrum E are defined to be the colimit of pi n plus k, number k, of E k? Yeah, it should be E k. Great. So the homotopy groups of the spectrum. We have generalized homology. Generalized homology. So given a spectrum E and another spectrum X, we're going to find the nth E homology group of X to simply be the colimit, again, taken over K of, oh wait, crap. I'm thinking of E as a spectrum here. Let me start that out. If we're given spectra E and X, we're going to define the nth E homology of X as the nth homotopy of X smash E. And in the case that we're thinking of E not as a spectrum, but as the reduced cohomology theory represents, we could also define the nth reduced cohomology with respect to E homology of X as an appropriate colimit of the E homology groups of the spaces in X. I'm not going to write all that out, but it's also in the notes, or will be at least. We can also have a generalized cohomology. So with the same setup as before, we can just define the and E cohomology groups of X as the set of map from the nth suspension of X into E. And we're going to say a spectrum is connective. if its homotopy groups are bounded below, we're going to say a spectrum has finite type if all the homotopy groups are finitely generated. And lastly, we're going to say it's finite if X is equivalent to the suspension spectrum of some finite complex. So for example, the sphere space. Great. Those are all the definitions I wanted to throw out there. Now back to homotopy directly. We're supposing we're given a collection of spectra X alpha, and given any collection, we can always form the coproduct, and it's more or less what we expect it to be given what the coproduct is in point spaces. And the operation of forming coproducts is well behaved. It commutes with smashing, so taking homotopy groups and whatnot. And the reason I want to start with coproducts, let me say, throughout we're going to note I would like to do a boldface X. Let me write it like that. I'm going to use this to note a directed system of spectra. We have X1, and so on. So we want to form the direct limit of this system. The reason I introduced the coproduct first is because I want to proceed an analogy to how we do things if everything were abelian groups. When we have a direct system of abelian groups, and we ask what is the co-limit of a directed system, it's kind of obvious what it should be. We can define. First of all, we take the coproduct of all the groups in question, and using the maps in the directed system, you sort of just know the maps give you an endomorphism of all of the coproduct of all the groups, a certain endomorphism that we define, and it's sort of tautological. The co-kernel of this self map, of this shift map we call it, should be the direct limit, should be the co-limit of this system. We want to do the same thing with spectra. Step one's done. We can form the coproduct of all these spaces. The problem is we can't on the nose define the shift map or take the co-kernel. What we're going to do is first, let me take this from my copy.
There's a question by Daron about your definition of finite spectrum. Could you scroll up to it again?
Oh. Yeah, 1 second.
So I believe the definition in Ravenel is that some suspension of it is equivalent to the suspension spectrum of a finite CW complex.
Some suspension of it is equivalent to the suspension.
Oh, interesting.
Oh, okay.
That would
That's
mean
what-
Ravenel's definition is also non-standard. But I suppose it's convention. I just wanted to mention this because when people say finite spectrum, usually they mean one which can be presented by a sequence of finite CW complexes, but not one which is necessarily equivalent to a suspension spectrum.
Wait, what do you mean by presented by a sequence?
As in, you can describe it as a sequential spectrum where every space in like each xn is a finite CW complex.
I see. Which might not necessarily be a suspension spectrum of a single finite complex.
Right. Right.
Okay.
Yeah, I only bring that up because finite spectra are they're going to be pretty important later on.
Maybe we should discuss this later to see if they're the same notion or if they differ. like one obvious thing that sounds different is when you just say each space is like a finite CW complex, it doesn't sound like such a thing has to be connective, but maybe it does because of the finiteness property. I don't know.
Well, I'll put a big red star there. There are, yeah. Anyway, so again, if I said if these were, oh, let me get the text out of the screen. I said if these were abelian groups, so if these were all AIs, we would take the coproduct of all the AIs, and we would define a self map of them, which I'll write as S, called the shift map. And it's simply given by take each element and send it to itself minus. And for one reason or another, once you define the self map on the big coproduct, it's tautological that its co-kernel will be the colon. And we want to do the same thing. And like I said, we have the coproduct of all these spectra. And I'm just going to say that there exists a map S from the coproduct of all these X to itself, which one could write out as a map on the level of all the wedges if you wanted to do that. And this map induces on the level of homology the shift map of abelian groups. So this is the map we want to think of as the shift map. And now we should ask, what is its co-kernel? And we don't have co-kernels here, but we do have our cofibers, or at least on the level of the spaces, we have cofibers. And when we ask something on the level of spaces, we ask, can we do the spectra? And in this case, the answer is yes. So I'll make the following definition. So if we're given a map of spectra, F from X to Y, we're going to write again CF for the cofiber spectrum of F. And I'm actually, let me not give the full definition. Somewhere in Atoms, you will find the full definition. I'll give the reference in the notes. But this is one of those nice constructions of spectra that on the level of the component spaces really is what you would expect it to be. So you take F, you replace all its component maps with cellular maps, and you just take cofibers at every nth level. And all the structure maps just pop out of the construction, and it gets the nice properties we want out of it. There are cofibers. That's the point. So, just taking from the top for a second, we have this directed system of spectra. We can form their coproduct. We can define a self-map of their coproduct, which induces the self-map whose co-kernel and abelian groups we know to be the co-limit of a directed system of abelian groups. And we know how to construct the analog of a co-kernel for spectra, namely the cofiber. So putting this all together, we can define the direct limit of the system. So Homotopy colimit of fold X is defined as follows. We're going to write this co-colon of fold X. It's going to be the cofiber of the shift map I claimed existed on the coproduct. And that's that. That is the homotopy colimit of this particular directed system. Now, this definition, immediately everything works more or less when you replace this direct system in particular with any directed system, not necessarily one that looks exactly like this. So, in general, directed systems of spectra have a homotopy colimit. Why do we call it a homotopy colimit? That's something not even I fully understand. But I can tell you something else about them, and that is that taking e-homology commutes with the formation of a homotopy colimit, so it's somewhat nicely behaved in that respect. And I can tell you something else about them, which makes me actually want to not call it a homotopy colimit. Maybe somebody can give me a better understanding of this. But the homotopy colimit is not a categorical limit. Namely, it doesn't have the right universal property. There is a long exact sequence by which you can study the pieces of the mappings. Oh, once again. Colons in the infinity category spectra. I trust that answer. I just wish to me, someone who doesn't understand the infinity category of spectra, when you call it a homotopy colimit, you would think it would behave as a colimit up to homotopy in the most basic way. But what Ravenel says makes it sound like it doesn't do that.
I mean, one of the reasons why it doesn't is because limits and colimits don't exist in the homotopy category. They're not well defined. If you take two spaces that have the same homotopy type and you replace them in the same diagram, you won't get the same answer. So the homotopy category just doesn't have limits and colimits, so you need to define the closest thing.
Yeah, if you want to be precise about it, but maybe not too precise, but limits and colimits in the homotopy category would be things that hold up to homotopy, whereas these hold up to coherent homotopy. Or natural homotopy, if you like.
Let me write that down because I want to remember what you said. Coherent homotopy, question mark. Great. Now wrapping up this proposition. It's not a categorical limit. It doesn't have the right universal property. We can give a long exact sequence between the pieces of the various homotopy classes of maps. This is written out in Ravenel. I'll write it out in the notes and I'll give a reference as well. I won't write it here. But I think maybe conceptually a more important point. If we have a compatible sequence of maps, system of maps, sorry, from the xi all to some other spectrum y, we do get a map from the homotopy colimit of the whole system to y, through which they factor. But this property of let me just say this in words. The property of being a map from the homotopy colimit to y, through which all these factor, does not even determine. So if we call this map G, this map right here, the property of being a map through which all the GI factor does not even determine this map up to homotopy. So we don't really have uniqueness here in any sense, in any good sense. It does not look like a good time to talk about homotopy inverse limits, so I'll be sure to have good notes on that. But let me wrap up with an important point. So here, let X be a finite. Actually, it doesn't have to be finite. That'd be silly. Be a CW spectrum. So we're just going to assume all the spaces really are. I guess anyway, let X be a CW spectrum. Now define a finite subspectrum simply be a map F of spectra F to X for any finite F. These are a category, a diagram in spectra. Maybe I should really write here a diagram in the obvious way. And this diagram is directed. And that is because given, well, first of all, given any two finite spectra, their smash is finite. And also because given any two maps from different finite spectra to space, so given F and G to, what are we calling it? We're calling it here X, we can form the wedge of F and G and these maps factor through it. Is that right? Yeah, that seems right. Should be the wedge. I might have things backwards. Anyway, this is the directed diagram of spectrum for pretty elementary reasons. So we have a directed system of spectra. We can ask about the homotopy colimit over all of these finite subspectra of X. Now, because of the way we define finite subspectra as literal maps into X, there is a canonical map from all of them to X. And therefore, we do get a map, call it lambda, from the homotopy colimit over all these finite subspectra to X. And statement of the proposition is that this map, lambda, is a weak homotopy equivalence. So we can say that a CW spectrum is, in a canonical way, weak homotopy equivalent to a homotopy colimit taken over its finite subspectra. Actually, I would recommend looking at the proof of this in Ravenel. It's not very hard. It's pretty, I found it very satisfying. And this is one of the, to me, I guess I can't speak much on how useful this really is, but I thought this was a conceptually pretty interesting point. Pretty much 10:50. I'm out of time. Let me state one more proposition. This is an important property and a useful property of the homotopy colimit. And the question we should ask before I state this is, how can we study the cohomology of a homotopy colimit? How well can we understand the cohomology of a homotopy colimit if we understand the cohomology of its pieces? And this is the Milnor short exact sequence. The Milnor sequence. For each integer n, we have a short exact sequence. The first term is this lim1 term of the cohomology of the spaces in X. So here E is any spectrum. The middle term will be the actual cohomology of the homotopy colimit, which maybe is the thing we ultimately want to understand in a lot of cases. And over on the right is the regular inverse limit of the inverse system of homology groups we get out of the spaces X dot. Great. And there's a couple elementary things you could derive right off the bat, just knowing that this Milnor short exact sequence is short exact. But I'll write those down in the notes and I'll give references and whatnot. Great. The only things I had left to talk about, which definitely don't have enough time to, first of all, are inverse limits, which are a little trickier than the direct limits. And also some of the basic structure for spectra, like what's a ring spectrum, what's a modular spectrum, how do we invert an element of the homotopy groups of a spectrum, and what is a flat ring spectrum? The only reason I mentioned this is because Ravenel defines flat, and Doran, I saw you talking about that on Discord. What was your terminal opinion of that?
So I talked about it on the Algebraic Topology Discord, and I also asked about it on Math Overflow. And the conclusion I came to is that it's not a great name, but Ravenel didn't have modern higher algebra. But essentially, the thing to keep in mind is that in Ravenel's definition, a ring spectrum E is flat if and only if E star E itself homology is free over pi star E. And this is a more useful definition than flatness and Lurie sense over the sphere spectrum, because there are almost no ring spectra which are actually flat over the sphere spectrum.
Okay.
Well, let's thank Matthew for the talk.
Woo. This was fun to prepare. To be honest, I had never looked through a lot of the details I wrote out today and which I had planned to write out. So this was very helpful for me.
Yeah. And are there any other questions we wanted to talk about?
Oh, I wanted to mention, I guess maybe for the benefit of the recording, but just I put this in the chat, but just a correction to what I said earlier. Ravenel's definition is in fact equivalent to the standard definition of a finite spectrum. You just have to mess around with it a little bit.
Really? I wouldn't guess that at all.
Yeah, so I stated it slightly incorrectly. It's not just that there's a finite number of cells in each dimension. There has to be a finite number of stable cells total. And you can essentially just say, well, take all the stable cells and then choose the representatives for them. And then that makes you a CW complex. You glue them together and then you suspend it.
Yeah, that makes more sense. Because maybe it is possible to construct a spectrum of finite CW complexes that's not connected, right? But that wouldn't be finite.
Right. Well, Ravenel sort of accounts for this by saying some appropriate suspension of it is a suspension spectrum. Because you can take a finite CW spectrum and sort of desuspend it until it's not connected anymore, but it'll always be bounded below, though.
Great. Well, thank you.
Yeah, thanks again. And next week, do we have, let's see, who do we have next week? Ding Long? Yeah, on formal groups.